We're ready now to implement a typed variant of Mo. So we're going to use as our expression grammar our usual small grammar, which is functions plus and times, including parenthesized things. But now our functions will explicitly annotate arguments with types. Right? So it's not optional. Unlike Shplait, you always have to write the type for a symbol. And then because you have to write a type, we need a grammar of types. So that can be either literally int, literally boolean, two types separated by an arrow, or you can wrap parentheses around types if you want to. Okay? Again, single argument functions, so an arrow always has just one type on its left. Translating that to a Shplait data type, our expression type looks mostly the same as it's always been, except that fun e has an extra piece in the middle, an arg type, that is an instance of the type. And then we define the type like this. So int t is the int type, bool t is the bool type, arrow t is the arrow type with two different types inside. For the type environment, we need a type binding, which maps a name to a type, and I'll call that constructor tbind. And then the type env is just a list of type bindings, and the same way that an environment was just a list of bindings. The typecheck function then takes an expression and an environment. I read it in the opposite order to the turnstile notation, but consistent order with the interp functions. So the expression is A, and the type environment is tm, and we just have to consider all the possible expressions. If it is an integer expression, we have a rule that tells us all integers are of type int. So we will just use int t as the result of typecheck in that case. Every integer does have a type, and the type is int. How about plus? Our rule for plus look like this. So we want to get an int out, but first we have to typecheck e1, and we have to typecheck e2, and we need to make sure that the results of those are int. Or put another way, we're writing a typecheck function, and we've got an expression. L is an expression, R is an expression, so our template tells us we probably want to typecheck both of those. And so whether we start from the rule or start from the design recipe, we get to the same sort of intermediate space here. But now we need to check that this type check for left, that reproduces the int type. If it doesn't, then we will complain. And instead of just using error directly, we're going to use a type error function that takes an expression and the type that it should have been and provides a nice error message. Meanwhile, if L does have type int, then we look at R and make sure that it is also of int. And if it is int, then both of them were int. We matched both pieces of this rule, so we can return the result int t. Otherwise, we complain about R not being of type int. Mult is similar, so we'll skip over that. But we'll look at identifiers now. An identifier has a name, and in the same way that interp of an identifier looks it up in the environment, type check of an identifier looks it up in the type environment. So type lookup is going to be directly analogous to lookup. That will give us a type, and that's the type we want to return. If we have a function expression, so here is our rule for type checking functions. You see that we will need to take the body expression and type check that. Again, just what we expect when we have an expression as a sub-expression, then we want to type check it. But the environment that we pass in is not just the environment that we got. Instead, we need to extend that environment tm that came in as the argument with the binding of the argument name to its type. That is, the function argument name in a funny and the argument type field of that funny. And then once we get that answer, we're not done because we don't just want to return t2, we want to return an arrow type, t1 arrow t2. And we construct that with arrow t using the arg type and the result we get back from typecheck. That just leaves application. So here's our rule for function calls or applications. We will type check both the argument and the function expressions. We need to make sure that the function expression is an arrow type. That is, we do a match on the type check of the function position to make sure we get an arrow t back. Arg type here corresponds to tal2 and result type corresponds to tal3. So as long as we get, if we don't get an arrow type, then we do a type error. But if we do get an arrow type, then now we need to look at E2. We don't require any specific type for that argument expression, but we do require that it matches the argument type of the arrow here. That is, we want the result of type check on the argument expression to match arg type in the arrow t. So we can compare them with equal, and as long as they're the same, and as long as this tal2 matches that tal2, then we want to return tal3, that is, we want to return result type here. If they don't match, then we complain with type error, saying that arg doesn't have the type that we expected for the arg type.